Hey everyone, we use electricity daily, whether it's for lighting our homes, enjoying music, or staying cool with fans and AC. Have you ever wondered how it all works? In this lesson, we'll explore electric charges in motion and how the flow of charge depends on the potential difference. We'll also look at Ohm's law, Kirchhoff's law, and potentiometer, a tool for measuring resistance and electromotive force. Let's get started. In today's video, we are diving deep into one of the fundamental concepts of electricity, electric current. In the last lesson, we studied that when a potential difference is applied across a conductor, an electric field is set up inside the conductor. Now, when this field is created, free electrons inside the conductor start moving. And guess what? This movement of electrons constitutes electric current. But here's the key point to remember. The conventional direction of current is taken as the direction in which the positive charges would move, even though electrons being negatively charged actually flow in the opposite direction. Let's break down the concept of electric current in detail. Imagine a conductor with an area A through which charge flows. The current is defined as the rate at which charge flows through a surface perpendicular to the direction of flow. Now, if charge del Q flows through this surface in a time interval del T, the average current is calculated as I average equal to del Q by del T. But if we want to know the instantaneous current, that is the current at any given moment in time, it is expressed as I is equal to dQ by dt. The electric current through a conductor is the rate of transfer of charge across a surface place normal to the direction of flow. The SI unit is ampere, symbolized by A. To put it simply, 1 ampere is the flow of 1 coulomb of charge passing through a conductor in 1 second. For smaller currents, we use units like milliampere and microampere. But what exactly causes this current? Well, it can arise from the flow of electrons, which are negative charges, especially in materials like metals. However, in semiconductors, current results from both electrons and holes. Holes are essentially vacancies in the crystal lattice of a semiconductor. These holes act as a positively charged particle and are crucial for understanding how current flows in semiconductors. Now, let us take a closer look at the flow of electrons in a conductor and derive the equation for current. Let us derive the equation of current for this conductor of cross-sectional area A. Consider this volume element of length del x. So the volume of this element is A times del x. If n is the number of electrons per unit volume, then the number of electrons in this volume element is n times A del x. If E is the charge on the electron, then the total charge in this volume element is given by del Q is equal to n times A del x E. If the electrons drift with the speed Vd due to thermal energy, the distance traveled in time del T is given by del x, which is Vt into del T. So, in substituting this value to del Q, we find that the total charge in the volume element under consideration is given by del Q is equal to n times A E Vd del T. From this, we can write del Q by del T is equal to n times A E Vd. This is the expression for current. Let's see an example. A total of 6 into 10 to the power 16 electrons pass through any cross section of a conducting wire per second. Determine the value of current in the wire. So here we can ignore the components like drift velocity and all. So the total charge del Q is n into E, which is 10 into 6 into 10 to the power 16 into the charge of the electron is 1.6 into 10 to the power minus 90. If we get 6 into 16 is 9.6 into 10 to the power minus 3. So I is equal to del Q by del T. Since it's given per second, 9 into 6 into 10 to the power minus 3. So we get this as 9.6 milliampere. To recap, electric current through any cross-sectional area is the rate of transfer of charge from one side to other side of the area. Unit of current is ampere and is denoted by A. The conventional direction of current is opposite to the flow of electrons. The current can be caused by the movement of electrons or holes depending on the material. We also derive the equation for current, which is I is equal to NAEVT, where the current is directly proportional to the drift velocity of the electrons, which is influenced by the applied electric field. Thank you for watching. If you found this video helpful, don't forget to like, share and subscribe. Have any questions? Comment below. I'll be happy to help.